What do you see here, Bobby?
I see two color, blue and red.
Blue and red.
And red seems to be better. What is red?
So, basically, what about these units here that you see? Maybe you get an idea about these.
Yeah, x-axis is frequency.
Yes.
Y-axis, you have some nanovolt per root hertz. I have not heard about this.
Bobby,
Nanovolt.
I think you're right.
Nanovolt, I know.
I think without considering this, you cannot make any sense. So then it's a good thing that we are going through this slide, because you never heard of this slide. So this is basically, if you look at any data sheet of a sensor, you'll see something called a section called noise characteristics, and you'll come across a graph like this.
Yes.
Right. Now in the search coil, we kind of analyzed the noise of the amplifier, the search it, right?
Yeah.
But we didn't really see what noise looks like if you analyze noise over, let's say, a frequency range.
Yeah.
Now, generally, to get a graph like this, what kind of instrument would you use to get a noise?
Number one, I will have to excite it for those frequency.
Okay, so...
Or is it...
No, you're right.
Yeah.
You're right. Which is why we have two frequencies here.
Okay.
So we are exciting... So imagine there's a Fluxgate.
Yeah.
That we're working, and
Correct.
we want to know the noise character.
Correct.
Then we, as you said, we excite it.
Yeah.
At two. In this case, we are exciting at two frequencies.
Yeah.
25 kilohertz and 50 kilohertz.
Okay.
Right? And then what we're doing is we are looking at the noise characteristics. Okay, over a range. So before that, there are...
So then that output is converted into frequency domain, and then look at the...
Exactly. Okay. Exactly. Because your noise is not the same at all frequencies.
Yes.
But before that, just to talk about a couple of other noise sources, right? So the demagnetizing factor adds some noise. I'm not talking about this graph, right? Specifically, but this has some sensor noise, right? And let's say NDB, core noise. So what I'm trying to say here is that your core, right? Let's say you assume your core is cylindrical, for example. It will not be perfectly cylindrical, right? It will not be 100% smooth. So there could be noise because of this anisotropy of the core, and that could add some noise, right? Now, if you look at this graph, you kind of see
it is reducing at a slope.
Yes, it's kind of somehow at some stage becoming something like this.
Correct.
Right? So this is your noise that you're trying to analyze, where you have nanovolts, so your output per root hertz of the frequency that you're measuring.
Okay.
So if you just kind of drag this, right? And say, move this down and move this down. We see 2 points here, right? And here, of course, there are different frequencies. Let's say we take so it could be actually at the same point. That's 4. Now here, we have a certain frequency where this kind of slope becomes straight, right? And this is our lowest frequency of interest. So this area, right, we call the 1F region.
Hmm.
This area.
So the noise is a bit more there.
Yes. I think there is also some other names, flicker noise,
Okay.
something like this, right? Anyway, this point here we call, this point here is known as the knee. Basically, if you extend this line,
Yeah.
and extend this straight line,
They touch.
they touch, and that point is called
Knee point.
knee point. And at that knee point, we have certain frequency. So I think this is 1, 2, 3, 4, 5. Yeah,
Okay.
right? So this gets 2 hertz.
Yeah.
And this FC, maybe I can put here. FC is what? That's the lowest frequency of interest in the 1/F region.
Mm-hmm.
Okay. Now, sorry. This is the lowest frequency. The cutoff frequency. Cutoff or the corner frequency.
Yeah.
Because it's at this corner.
Correct.
Now, let's say you are measuring from here. Like you can measure from anywhere you like,
Mm-hmm.
right? And this is called FL. And this is the lowest frequency of interest in the 1F region. Okay, this is your 1F region. This is your cutoff or corner frequency. This is the lowest frequency. So you want to kind of, let's say, have the lowest frequency. You can even have it from here. It doesn't matter, right? You choose. And your highest frequency is, let's say, here. At the end of this, you have FH. Now, FH is the highest frequency of interest. Now, what do you see in this part here, Boby? This part here.
It's almost flat, and they are
Just kind of going up and down,
Yeah.
and down, right?
it's like a noise signal.
It's like a noisy signal.
Yes.
Right?
Yeah.
So in fact, you're right. This is noise that we cannot get rid of.
Yeah.
Even if you have the best circuits in
Yeah.
the world.
Yeah.
And that's called white noise. In fact, for flux gates, and we talked about this with the surge coils, the dominating the dominant white noise in this case is thermal noise.
Yeah.
Now the thermal noise, let's say if you call it white, is, we already know, is 4kTr. Remember that?
Yeah.
Plus, I am sure you remember this too. That's the voltage, spectral density of the amplifier. Remember in the search part, which you already analyzed this.
Yeah.
And we know what this is.
Correct.
So this part here.
Yeah.
Right?
It's a 4 kTr, no?
4 kTr.
Yeah. There was some term bandwidth also.
Yeah, and Boltzmann constant.
Yeah.
When that?
Yeah.
4 kTb.
Correct.
4 kTb, right?
Yeah.
Am I right? Yes. 4 kTb. I forget the equation now.
Yeah.
But that's thermal noise that
Yes.
we had before.
Yes.
Right?
Yes.
Yeah.
So
Yes.
maybe we can just erase and write that thermal noise.
Yes. But yes, this, huh?
Yeah.
The thermal noise we did in the class.
Yeah.
I forget the equation. Yeah. But anyway, it's easy to find, right? Okay, let's get back to this. Now, if you look at Vn, noise, RMS, in this 1 over F region, okay? It's basically you have to integrate, right? From here to the corner frequency, 1 over F df. Then you get VNW square root of FC natural log FC over FL. Correct? I'm talking about this region here.
Yeah.
Right? So all the area underneath.
Yeah.
Then you have your Vn RMS in this region is what? Simply the FH minus FC. Yes, FH minus FC, which is this region here. Right? So for this region we have this.
Yeah.
And for this region we have this.
Yeah.
So then the total noise is
square root of these two.
Exactly. Is VNW square root of FCLN FC over FL, sorry, plus FH minus FC. So by using this, we can estimate the total noise in this frequency range. Gives an idea of how well our sensor is working. So there's another for Fluxgates. There's also another noise source called Barkhausen noise.
This is from the core or?
Yes.
Okay.
Yes. Would you like to explain? Yes, it is from the core. You're right. So whereas, you know the BH curve, right? So what we're trying to do is we are trying to magnetize the core. Now the core has domains.
Yeah.
Right.
I remember you explaining some time back.
Yeah. And sometimes the domains kind of when the magnetic moments, when they switch, right, your domain walls expand, but sometimes there are some certain points where they get stuck. Now, when they get stuck and you keep applying a magnetic field, they kind of pop. And in fact, with Fluxgates, you can actually hear that noise.
Yes. Here means
you get. Yes, surprisingly, so basically,
so we will have to convert this output into a audio.
Yes, so you can actually see it as electric pulses.
Correct.
Right? This Barkhausen noise. But
so that means your noise of your system, measurement system is very low. That you are able to.
Yes.
Yeah.
But general Fluxgates are very low, right?
Correct.
So either you can see it or you can
convert into audio and hear it.
But that kind of thing you cannot avoid, right?
Yeah.
But I think those signatures are very unique. You probably can get rid of those signatures in the sense that when you analyze the signal, you know that is not to do with the magnetic field they're trying to measure, right? What else? Oh, there is also the minimum detectable signal, right? So for any Fluxgate.
For example, if it is something in femtotesla, it may not be able to sense.
Yes. So there is also this other way that
to
can get
estimate
indication of the minimum detectable magnetic field. It's a paper here that talks about it. So here, what basically
are they giving some equation to estimate?
Yes. So obviously you have your graph, so you have a very good idea about your
Yeah.
noise.
But even without this, it may be
Even
possible.
without this, and even with this, you might even compare this to what you can
Got
measure, right? So let's say this is what you're trying to measure. This is your minimum detectable signal. Okay?
Yeah.
Is equal to PS, which is your saturation magnetic flux density. Here by mu is your mu r. Okay? Square root of tau or tau.
What is tau?
So tau is the inverse of the excitation frequency.
Okay.
Okay? And then we have NB. We had it ND, no, before? Yes.
Yeah.
That's your NB. This is NB. And there's also TM. TM is the measurement time. So you're making a measurement. How long is the
duration of the measurement?
Duration of the measurement. NB, we talked about Barkhausen.
Okay.
Right? And that's there's something called Barkhausen volume. And that's experimentally found to be 10 to the 4.
Okay.
Right? Again, something that been found by experiments. But the key point here is now
for some specified material.
For some specified core material.
Core material.
Yes. So if your tau is 10 to the minus 6, right? So what's that? 1,000 kilohertz. Right? 1,000 kilohertz. Let's say you're measuring it for 1 second.
1 second.
1 second.
Okay.
And then your mu r is, let's say, 8,000. Then the minimum detectable range will be 2 picotesla.
Okay. Yep. Picotesla.
Right? So another indication of how low you can measure.
Yeah.
Using that.
So earth magnetic field is like 50-60 microtesla. This is picotesla.
So in fact, Fluxgates are used to measure very low magnetic fields.
Nanotesla range.
Yes, nanotesla. I guess
this is the resolution, picotesla.
This is the minimum detectable. Yes, so resolution.
Correct.
Yes. Yes. Okay. So just again, for the surge coils, again, if you look at the surge coil, you get a graph like this for the noise, right? You can use the same techniques that we talked about today to calculate the total noise of your system, right? Of course, you can, the part about the amplifier we already know. So similarly, you can calculate the total noise of the measurement instrument that you're designing.